Hundreds of thousands of clay tablets sit in museum drawers covered in wedge marks almost nobody alive can read. Learning the script normally takes a decade of training. Then a small computer science team in Israel, not trained linguists, pointed a language model at the wedges instead. It found something that made trained scholars stop and take notice. Cuneiform is one of the oldest writing systems people have ever found, going back to around 3400 BCE. It was pressed into wet clay using a reed stylus, leaving behind small wedge-shaped marks. Over the centuries, this script was used to write several different languages, most importantly, Sumerian and Akkadian. Sumerian has no known relatives anywhere on Earth, and it was spoken in the southern part of what is now Iraq, starting around 4500 BCE. Akkadian came later and became the common language of trade and government across the whole region, used by Assyrians and Babylonians alike for thousands of years. Archaeologists have dug up so many of these tablets that nobody can even count them accurately anymore, with estimates running into the hundreds of thousands. The problem is that reading Akkadian or Sumerian takes years of specialized training, and there are only a small number of people on Earth who can do it well. Most tablets sit untouched in storage simply because there is nobody available to read them. That gap between how many tablets exist and how few people can read them is exactly what pulled computer scientists into this field in the first place. And their solution started with a very simple idea, borrowed from Google Translate. In May 2023, a team from Tel Aviv University and Ariel University published a study in a peer-reviewed science journal called PNAS Nexus. The researchers were Guy Guthers, Shai Gordon, Luis Science, Omer Levy, and Jonathan Berendt. Their project started small, as a thesis Guthers was writing for his master's degree, before it grew into a full research paper. What they built was a neural machine translation model, the same basic technology behind Google Translate, except trained specifically to turn Akkadian into English. The model worked by studying thousands of Akkadian texts that scholars had already translated by hand over the decades, mostly pulled from a project called the Open Richly Annotated Cuneiform Corpus. By comparing the original Akkadian against the human translation side by side, the computer slowly learned patterns in grammar and word choice, the same way a person might pick up a new language by reading a stack of bilingual books. That basic setup sounds simple enough on paper, but actually getting a computer to handle a language nobody speaks anymore, with barely any digital text to learn from, turned into a far harder technical puzzle than anyone expected going in. The team built two separate versions of their program. One version read Akkadian in its transliterated form, meaning the sounds of the words written out in our alphabet. The other version tried something much harder, reading the actual Unicode symbols of the cuneiform signs directly, without any human translating the wedges into letters first. The transliteration version worked noticeably better. When researchers scored it using a standard translation quality test called Blue 4, it came out with a score of 37.47, a number that put it in the range experts consider a genuinely useful translation. The program worked best on short and medium-length sentences, particularly formal writing like royal decrees, government records, and legal documents, since those follow fairly predictable patterns. Dr. Gordon said the tool worked well enough that even a rough translation from the machine could save a scholar significant time, letting them start from a decent draft instead of starting from nothing. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. That success came with some real limits too, though, and the honest flaws in the system turned out to matter just as much to the story as its strengths did. The researchers were upfront that their tool was not a replacement for trained experts. It struggled with longer sentences, generally performing worse once a passage passed roughly 118 characters. It also sometimes produced what the team called hallucinations, meaning the output read as a perfectly normal, grammatically correct English sentence that simply was not an accurate translation of the actual Akkadian underneath it. The system had no way of flagging when this happened, so a person still had to check its work. Because of this, the team described their tool as a form of human-machine collaboration rather than a full replacement for human translators. A researcher could feed in a tablet, get back a rough English draft in seconds, and then spend their remaining time correcting and refining that draft instead of building a translation completely from scratch. For scholars facing a backlog of hundreds of thousands of untranslated tablets, even that partial shortcut mattered enormously. Reading whole tablets was only half the challenge, though, since many tablets that survive today are broken, cracked, or missing entire chunks of text. And a separate team had already been working on that exact problem years earlier. Long before the translation study came out, a different group of researchers had tackled a related problem. What happens when a tablet is simply broken and pieces of the writing are gone forever? In 2020, Ethan Fataya, Yonatan Lifshitz, Elad Aaron, and Shay Gordon published a study in the journal PNAS describing a system built using recurrent neural networks, a type of AI good at predicting what comes next in a sequence. Their model focused on Akkadian texts from the Achaemenid period of Babylon, a stretch of history running from around the 6th century BCE onward. Traditionally, filling in a damaged section of a tablet required an expert to manually compare it against similar surviving texts, a slow process that only a handful of people in the world are qualified to do. The team system reached an accuracy of up to 97% when it came to automatically transliterating and separating the cuneiform signs into individual words. For predicting an actual missing word in a damaged sentence, the system performed best on smaller gaps, though its accuracy dropped once 2 or more words needed to be guessed at the same time in different spots. The researchers eventually planned to build this work into an online tool named Atrahasis, meant to help scholars and students reconstruct broken passages more quickly. That project solved the problem of missing words, but it still relied on someone having already turned the photograph of a tablet into readable, transliterated text in the first place. And that particular step turned out to be its own massive bottleneck. Before any AI can translate or restore a tablet, something has to first recognize which wedge-shaped marks are actually there. That is a much harder task than it sounds, since cuneiform tablets are physical, three-dimensional objects, and a flat photograph often loses crucial depth information depending on the angle of the light. A team led by computer scientist Hubert Mara, working with researchers Ernst Stotzner and Timo Homburg at universities in Heidelberg and Halle in Germany, built a system to solve exactly that. Their approach used a type of AI model called a region-based convolutional neural network, more commonly shortened to RCNN, a technology originally designed for recognizing objects in ordinary photos. Instead of training it on flat photographs alone, the team fed it three-dimensional scans of real tablets, captured using specialized scanning software the group had developed. They built two datasets for this work, named HiQubidae and MyQubidae, made up of around 500 annotated tablets from real museum collections, including the Hilprecht collection in Germany. Inside these datasets, the team manually labeled roughly 21,000 individual cuneiform signs, along with thousands of the smaller wedge shapes that make up each sign. Mara explained that until this system existed, working with cuneiform meant you basically had to already know what you were searching for and where to find it. His team's system changed that by making it possible to scan through the shapes of thousands of tablets automatically, without a person needing to inspect each one by hand first. Between these three separate projects, the tools now existed to scan a tablet, recognize its signs, translate its words, and fill in whatever pieces were missing. But once headlines about AI and ancient texts started spreading online, a very different and far less accurate version of this story began circulating instead. Search around online today, and you will find a flood of videos and articles claiming AI has uncovered shocking secrets buried in Sumerian tablets, hidden warnings about ancient astronauts, or proof of beings called the Anunnaki genetically engineering early humans. Some of these posts claim researchers found phrases like essence mixture or prototype yield buried in translated texts, framing ordinary Mesopotamian creation myths as coded science documents. None of the actual published research supports any of this. The real AI studies were built to translate known administrative records, legal documents, and literary texts that scholars had already been studying for well over a century, using traditional methods. Sumerian mythology absolutely does include stories about gods shaping humans out of clay, and the Sumerian king list absolutely does describe certain early rulers reigning for tens of thousands of years. Historians have known about both of these things since cuneiform was first deciphered back in the 1800s, long before any computer got involved. Scholars generally treat those enormous reign lengths as symbolic, rather than literal, tied to number systems and ideas about kingship, rather than a record of actual events. The genuine research papers themselves are careful and modest about what their tools can do. One recent overview of the field put it plainly, saying that AI does not suddenly solve ancient mysteries, but it does let researchers revisit texts that were once considered too damaged or obscure to bother with. That is a much smaller and far less dramatic claim than what shows up in most viral posts about the topic, but it happens to be the version that is actually true. That gap between the careful, peer-reviewed science and the sensational online claims says a lot about where this story stands today, and it points toward what these tools are really likely to change going forward. Taken together, these projects represent a real and meaningful shift in how scholars study one of humanity's oldest writing systems. A neural network out of Tel Aviv and Ariel University can now produce a usable rough translation of Akkadian text in seconds, something that once required years of specialized training. A separate system built by researchers including Ethan Fataya and Shay Gordon can predict missing words in damaged tablets with striking accuracy. A third system out of Heidelberg and Halle can scan three-dimensional models of tablets and automatically detect individual cuneiform signs, opening up collections that had been effectively unreadable simply because nobody had the time to look through them sign by sign. None of these tools work perfectly on their own, and every research team involved has said clearly that human experts still need to check the output. The translation model still produces occasional hallucinations that sound convincing but are wrong. The restoration model still struggles. Once too many words are missing at once. None of the genuine research has turned up any hidden warning from an ancient civilization, any secret about ancient astronauts, or any lost genetic code buried in a clay tablet. What it has actually produced is something quieter, but arguably more valuable. A set of practical tools that could let a much larger group of people finally read texts that sat untouched for thousands of years simply because there weren't enough trained scholars to get to them all. The tablets themselves have not changed. What changed is how many people can finally start reading what they say. If this kind of deep dive is something you want more of, subscribing costs nothing and keeps this channel digging up stories like it.